And welcome back. I'm very pleased to have on the line with us Professor Peter Wadhams. He's a professor of ocean physics, head of the Polar Ocean Physics Group at the Department of Applied Mathematics and Theoretical Physics at the University of Cambridge in the United Kingdom. And he has just done some extraordinary work. He's in the video that we did with Leo DiCaprio on carbon and methane. Professor Wadhams, welcome to the program.
Good evening. Yes, nice to be here.
So pleased to have you with us, and thank you for staying up late and coming in. You've written about an ice-free Arctic, the possibility. You predicted, the data has indicated that within the next few years, the Arctic will be completely ice-free for the first time in over 100,000 years. What are the consequences of that, the people on this planet?
Well, there's a whole series of consequences, which are all, unfortunately, rather serious. Firstly, the retreat of the sea ice or the loss of the summer sea ice will mean that global warming will increase because you're changing a large area of white to dark. So you're reducing the average albedo of the planet, and that will mean that it's absorbing more radiation in summer through having a big area of open water in the Arctic. And that means that global warming will accelerate. Secondly, there's going to be an acceleration of sea level rise because the warm air that's lying over this open water in the Arctic Ocean moves in over the island of Greenland and gives you surface melt of the Greenland ice sheet to an extent which didn't used to happen. We now found in 2012, for instance, that the entire surface of the Greenland ice sheet was starting to melt for a period in the summer, which is completely new. And this will mean that sea level rise will be accelerated because that meltwater runs off into the ocean. Possibly one of the most severe threats is the fact that the shallow waters off the Arctic coasts, especially the Siberian coasts, where there's very wide continental shelves with only about 50 to 100 meters of water depth, that water can warm up during the summer months because the area is now ice-free, already ice-free. And this gives you positive temperatures on the seabed, which start to thaw out the seabed permafrost, which has been sitting there frozen since before the last ice age. This has never happened before, and because the sea ice never retreated very much in summer, so the water temperature couldn't rise above zero because there was still ice sitting there on the surface. With the ice gone, the water can warm up. The warming water thaws the permafrost, and the permafrost is acting as a cap for a very large amount of methane, which is sitting in the sediments underneath in the form of methane hydrates. So you release the pressure by releasing that permafrost. This methane comes out as huge bubble plumes. That's already happening. It's been detected by scientists all over the Russian Arctic, most recently by a Swedish expedition, before that by various US-Russian expeditions. Each time they go, there's more and more bubbles, plumes coming out. And the fear is that there'll be a general release of methane trapped under those sediments, which could cause a very rapid rise in the rate of sea level. We calculated it could give you 0.6 of a degree warming of the planet in 5 years. That's a really a big boost because methane is such a powerful greenhouse gas. So I think we must be really afraid of a methane pulse.
So if methane pulse or a surge or explosion is the wrong word, but because it implies combustion, but the sudden release of methane from the sea level, the seabed, and the permafrost around it as well, and the permafrost under it. Hasn't that in the past, in the Permian and the PETM and others, been associated with extinction events?
Well, yes, in the sense that extinction events happened and nobody was quite sure what caused them. So methane has been advanced as a possible cause because it doesn't leave any traces behind it. It's like the perfect murder weapon. It's within about 7 to 10 years of release, it gets oxidized in the atmosphere, so that it doesn't stay around. It does its dirty work, and then it turns into carbon dioxide. Whereas carbon dioxide itself stays around, and that's really the problem that we're having with global warming, is that the carbon dioxide we release now remains in the Earth's climate system for hundreds of years, and so it builds up. We're having to live with the carbon dioxide released by factories in the 1920s, and the future people will have to live with our carbon dioxide. But methane is a very powerful greenhouse gas, but it's short-lived. So it could have been possible that it was responsible for some of these early events, but we don't know. And I think it's been fingered as the villain because it doesn't leave any traces behind it. So we can't be sure what happened, really.
So what do you say to people who call predictions of rapid global climate change alarmists? And how rapid is this change that we've been witnessing over the last 100 or so years relative to previous global warming events that we know about from the geological record?
Well, I suppose I'm trying to think of a word for the opposite of an alarmist, a complacentist, I suppose, because I think they're being possibly dangerously complacent, because if the view that nothing much is happening, or what is happening is happening slowly, when that view is transmitted to governments and used in planning, then it leads to a complacency in the sense that you don't need to do anything very urgently, because you just watch what's happening and then you start to take measures when things get serious. But in fact, things are getting serious now, and if we don't take action now, they'll be getting more serious more rapidly than we can cope with. So it certainly is the case that the rate of warming is now far greater than anything we had before, and it's something that is accelerating, and new processes are coming into play. I think that's the thing that's most worrying, that as well as the feedback processes that were happening that related to our carbon emissions, we're now having extra feedbacks from the changes that the warming has itself produced. So we find, for instance, that the warming of the Arctic, the loss of ice from the Arctic, then leads on to accelerated warming because of albedo, to accelerated sea level rise, and to possible methane burst that will itself cause accelerated warming. So already an analysis that was done at Scripps Institute of Oceanography showed that just the retreat of sea ice is equivalent to adding a quarter to the amount of carbon dioxide that we release into the atmosphere. And if you add the snowline retreat, it makes it a half. So what we're doing, every 2 molecules of carbon dioxide we put into the atmosphere, we get another free extra molecule added from these feedbacks. And that's what's very worrying, is that we're now getting feedbacks almost beginning to dominate the warming process.
Wow. Is this, Professor Wadhams, we have a little less than 20 seconds left. Is there any chance you could stick around with us for a little bit and talk?
Yes, certainly, yes.
Oh, that would be wonderful. Thank you so much. This is a very, very concerning thing. What I want to get into is the question of tipping points. We'll talk about that right after the break. With us is Professor Peter Wadhams, Professor of Ocean Physics, head of the Polar Ocean Physics Group at the Department of Applied Mathematics and Theoretical Physics at the University of Cambridge in the United Kingdom. The website and contact information, Twitter information, all that is on our website. You can tweet at Cambridge_UNI, and we're talking about an ice-free Arctic. Stick around.
This is the Thom Hartmann Program.
Massive changes in the Arctic that you need to know about. Stick around. And welcome back. Professor Wadhams, you're still with us?
Yes, I'm here.
Oh, great. So tipping points are difficult to pin down, and very often you don't realize that you've passed a tipping point until you see it retrospectively. What are the major tipping points that we need to be concerned about and that we're heading towards or that we might have already passed?
Well, I think the word tipping point is often used kind of loosely, but I think a rigorous definition is it's a bit like pulling on what you study at school, pulling on a spring, and it snaps back elastically up to a point, and then you put too big a load on it, it never goes back again. You've changed the structure of the spring. And I think a tipping point in the Arctic would be where if you tried to get the climate back to where it was before, it wouldn't go back. It won't go back again to where it was before. It will go into some new system. And I think in a way, we've passed certain tipping points. For instance, I don't think when the summer sea ice goes completely, it's not going to come back. I mean, it comes back in winter. We'll get winter growth of sea ice again, like we get in the Antarctic. We have the summer sea ice mostly melts, but it comes back again in winter. So we'll have winter sea ice growing again in the Arctic, but we won't have summer sea ice because the opening of such a large area of water absorbs a huge amount of heat into the ocean, and that delays any freeze up the next winter, and the ice doesn't grow as thick and it breaks up again earlier. So I think you can be pretty sure that if the ice goes in the summer, it won't come back in the summer, that the summer window of open water will remain and will probably grow wider within 2 or 3 years after after September is ice-free. We'll be having July, August and October ice-free. So we're going to be seeing a growth of the summer open water. And then that's in itself a tipping point. Another tipping point is the fact that multi-year ice, which is the very heavy ice that used to dominate in the Arctic, it just won't come back because there isn't the opportunity for ice to remain more than 1 year in the Arctic. So we'll never again see the massive ice flows and pressure ridges that I used to walk around on and sail under in the 70s and 80s. So that's a tipping point as well.
This is remarkable stuff. What we have just a minute until the break. May I ask you for another 6 minutes after that? Can we?
Yes, and if you like, I could, like everybody who comes on TV, advertise my book.
Oh yes, please.
About to publish a book called A Farewell to Ice with Penguin Random House, and this is coming out in September, and it deals with the disappearance of sea ice and all these consequences that are flowing from that, and has a bit of personal history in as well.
Marvelous. Farewell to Ice is the book. It'll be out in September, and
I stole the title from Ernest Hemingway.
Farewell to Arms, right? Yeah, that's a very literate title, as well as a fascinating one. Stick around just a second. We'll come back and we'll talk with a little more about this. Professor Peter Wadhams is with us. He is the professor of ocean physics and head of the Polar Ocean Physics Group at the Department of Applied Mathematics and Theoretical Physics at the University of Cambridge. We'll be right back. It is 20 minutes past the hour. Welcome back. Thom Hartmann here with you. And on the line with us is Professor Peter Wadhams. He is the professor of ocean physics, head of the Polar Ocean Physics Group at the Department of Applied Mathematics and Theoretical Physics at the University of Cambridge in the UK. The author of a book coming out this September titled Farewell to Ice. And it's not just an homage to Ernest Hemingway. It's about ice, right, in the Arctic. And Professor Wadhams, we were just talking about tipping points, and you said that as I recall, that we've pretty much passed the tipping point for a loss of summer sea ice in the Arctic, and we're starting to, and you mentioned, we're getting a third molecule of carbon dioxide for every 2 that we emit as a consequence of at least that one primary feedback loop of loss of albedo, loss of reflectivity up in the Arctic. Where does this end? And on this, there's kind of a spectrum of folks speaking about these issues. On one far end, you've got folks like Guy McPherson who are saying, okay, we're all going to die in 100 years, and not from biological I mean, the planet's going to die. And so just, get ready to say goodbye because it's gone too far. And then on the other hand, you've got people, who even continue to deny that climate change is happening at all. What's, in terms of risks, where are we really at right now?
Well, in terms of risks, I'm afraid we're more towards the McPherson's end, but I don't think we need to despair the way he does. The reason is that we can, I feel like many people do, that the idea of reducing carbon emissions as vigorously as we can, it obviously has to be done, but it's kind of hopeless that this will solve our problems. If the Intergovernmental Panel on Climate Change says we need to stay below 2 degrees or even 1.5 degrees of warming, we're just not going to make that by reducing carbon dioxide emissions alone, because they're so built into our society and even the fabric of our cities and our civilization. We depend on fossil fuels, and we can reduce them, and we can take a lot of steps to reduce the emission of them, but it will take time and it will be much slower than anybody thinks. So in that sense, it looks as if we're doomed. But there are two things we can do where the kind of native skills and intelligence of especially of Americans could really come and save us. There's a sort of a go-go approach that's needed here, and that's geoengineering and carbon drawdown. These are the two things. We have to take carbon out of the atmosphere. We can't just try to reduce the emission of it, because we've already got too much carbon dioxide in the atmosphere. So if we can put a sticking plaster on it by geoengineering methods like marine cloud brightening, which I personally like because you're putting water vapor into clouds, which is a harmless thing to do, as opposed to putting powders into the stratosphere, that can slow global warming. But to actually bring it to a halt and give us a future, you have to design and devise ways of air capture of carbon dioxide, ways of taking carbon dioxide directly out of the atmosphere and putting it somewhere where it can't, where it's out of the system. And that's a technical problem, and it can be solved. You need a project of the scale of the Manhattan Project, but it's the future of the planet, so it's something which ought to be done, and I think people should come to realize that that's the thing that has to be done. We can't mess around with halfway things like reducing our carbon dioxide emissions, because we're just not going to do it. We can say we'll do it, and what politicians can say they'll do it, and they'll with their hands on their hearts, but they won't do it, and we won't do it, not fast enough. But carbon dioxide, taking it out of the atmosphere, whether it's by these sort of artificial trees or whatever idea, should be vigorously pursued, and that's what's needed to save us, to actually bring the carbon dioxide level down. That's the only thing that ultimately will keep us going. So that should be our main research effort in science, I think.
And by save us, are you talking about the end of a habitable planet for humans?
Yes, I am, really, because it's a kind of a perfect sort of perfect storm of bad things is going on because of the exponential increases of all the bad things. So population still increasing exponentially, food supply can only increase to a certain level because of we've only got one Earth. We're increasing our with all the increasing of emissions, we're warming our climate rapidly. There's a lots of, and we're running out of water. Wherever you see changes, they're always going in the wrong direction. And the only way to bring them to a halt is to actually stop the climate warming. And without that, something will come against the buffers somewhere, either in warfare or lack of water, lack of food. Something will bring about a collapse or rise of sea level, which could bring about an economic collapse. Or we'll come up against something that will bring us down as a society if we don't work to actually stop the warming going on.
Right. And we have a little less than a minute left. We have to take the carbon out of the oceans too, don't we? Isn't it killing the oceans, all this carbonic acid?
Well, yes, but in fact, the oceans, it's very important that there should be carbon dissolved in the oceans, just because that's a big reservoir. One of the fears at the moment is that the ocean's capacity for absorbing carbon dioxide seems to be slowing, and less of what we emit goes into the ocean, more of it stays in the atmosphere.
Mm. And so that's another positive feedback loop that for a bad thing.
Yes, I'm afraid so, yes.
More rapidly increasing the temperature of our atmosphere. That's absolutely remarkable. Your book is going to be published in September, A Farewell to Ice by Penguin. And people can find it, I'm sure, at all the normal sources. We'll talk about it again when the book is out. I'd love to have you back. Professor Wadhams, thank you so much for being with us today.
My pleasure.
Great talking with you. Professor Peter Wadhams, Professor of Ocean Physics, head of the Polar Ocean Physics Group at the Department of Applied Mathematics and Theoretical Physics at the University of Cambridge. We'll be back with your calls after this.
You're listening to the Thom Hartmann Program.
To watch more clips from our programs, hit the Watch More Videos button over here. And please be sure to hit the handy-dandy subscribe button so you'll always be up to date. Tag, you're it.